Welcome to DAR Tutors. We provide expert online and home tuition for IB, A-Level, and IGCSE curricula. Today, we're going to delve into a fundamental concept in thermochemistry, Hess's law. We will explore its applications, learn how to calculate enthalpy changes using standard formation and combustion data, and then apply these principles to construct Born-Haber cycles for ionic compounds. Our goal is to equip you with the skills to solve HL-level problems related to these topics. Let's begin with the application of Hess's law using enthalpies of formation. Hess's law states that the total enthalpy change for a reaction is independent of the pathway taken. This is a direct consequence of enthalpy being a state function. We can visualize this with a Hess cycle. Consider a reaction converting reactants into products. This reaction has an enthalpy change of dH. Now imagine an alternative two-step pathway. First, the reactants decompose into their constituent elements. Second, these elements then recombine to form the products. For any pathway between 2 points, the total enthalpy change must be the same. The first step, going from reactants to elements, is the reverse of a formation reaction. So, its enthalpy change is the negative of the sum of the standard enthalpies of formation of the reactants. The second step, forming products from elements, is simply the sum of the standard enthalpies of formation of the products. By Hess's law, the direct pathway dH must equal the alternative pathway, which is dH1 plus dH2. This gives us the general formula. dH is the sum of the formation enthalpies of the products minus the sum of the formation enthalpies of the reactants. It's crucial to remember that formation enthalpies of elements in their standard states, like O2 or Al, are defined as 0. Let's work through an example. We will calculate the enthalpy change for a redox reaction. We need to find the enthalpy change for the reaction of 3 moles of solid copper, 2 oxide with 2 moles of solid aluminum, forming 3 moles of solid copper and 1 mole of solid aluminum oxide. We are given the standard enthalpies of formation for copper 2 oxide and aluminum oxide. First, let's write down the balanced equation and list the enthalpies of formation. For aluminum and copper, which are elements in their standard states, their formation enthalpies are 0. We apply our formula. Delta H is the sum of product formation enthalpies minus the sum of reactant formation enthalpies. Now we substitute the values. The product side is 3 times 0 for copper, plus negative 1,669 for aluminum oxide. The reactant side is 3 times negative 155 for copper oxide, plus 2 times 0 for aluminum. This simplifies to negative 1,669 minus negative 465, which is negative 1,204 kilojoules per mole. The negative sign indicates that this reaction is exothermic. We can also calculate enthalpy changes using standard enthalpies of combustion. Enthalpy of combustion is the heat released when 1 mole of a substance is completely burned in oxygen under standard conditions. Almost all combustion reactions are exothermic. The Hess cycle for combustion is different from the formation cycle. Here, the elements are not the common intermediate. Instead, we burn both the reactants and the products completely to form the same combustion products, typically CO2 and H2O. The arrows for combustion enthalpies point downwards as they are exothermic. Following Hess's law, the sum of the top path equals the sum of the bottom path. This gives us the equation. dH of the reaction is the sum of the combustion enthalpies of the reactants minus the sum of the combustion enthalpies of the products. A key point to notice is the sign flip. For formation, it's products minus reactants. For combustion, it's reactants minus products. This difference arises because of the direction of the arrows in the respective Hess cycles. Let's apply the combustion formula to an example. We're asked to find the enthalpy change for the hydrogenation of propene to propane, given the combustion enthalpies of the 3 organic compounds. First, we list our reactants and products and their combustion enthalpies. Remember, the formula is the sum of reactants' combustion enthalpies minus the sum of products' combustion enthalpies. Let's plug in our values. The reactants are propene and hydrogen, so we add their combustion enthalpies. The product is propane, so we subtract its combustion enthalpy. Adding the reactant values gives negative 2344. Subtracting negative 2219 is the same as adding positive 2219. The result is negative 125 kilojoules per mole. Now let's broaden our view of enthalpy changes. While formation and combustion are key, they are just two types among many. Here we see a table of various standard enthalpy changes. Each one describes the energy change associated with a specific type of chemical or physical transition. For instance, fusion is the melting of a solid and it's endothermic. A particularly important type for ionic compounds is lattice enthalpy. Lattice enthalpy, often symbolized as delta HL, is the energy required to break 1 mole of an ionic compound into its component gaseous ions, separating them to an infinite distance. It's the measure of the strength of the ionic bonds in the lattice. The process is always endothermic, meaning energy must be supplied. Why? Because we are overcoming strong electrostatic attractions between the oppositely charged ions. The animation shows a calcium fluoride lattice. When energy is added, the strong ionic bonds are broken, and the ions separate into a gaseous state. The magnitude of lattice enthalpy is influenced by two main factors: the charge on the ions and the distance between their centers. The formula is based on Coulomb's law. Coulomb's law states that the force of attraction is directly proportional to the product of the charges and inversely proportional to the square of the distance. Therefore, high charges and small ionic radii lead to a strong attraction and a large positive lattice enthalpy. Lattice enthalpy cannot be measured directly, so we use a Born-Haber cycle. This cycle is a visual representation of Hess's law for ionic compound formation. The cycle consists of a direct path of formation from elements to the ionic solid and an indirect multi-step path involving atomization, ionization, and electron affinity to convert the elements into gaseous ions, followed by lattice formation. Let's construct one for sodium chloride. The cycle starts with solid sodium and chlorine gas. The first step is atomization, converting the elements into gaseous atoms. This is endothermic. Second, ionization, forming gaseous cations from the metal atoms, is also endothermic. Third, electron affinity, forming gaseous anions from the non-metal atoms, is typically exothermic for the first electron. We apply Hess's law. The sum of the enthalpy changes in the direct pathway equals the sum of the enthalpy changes in the indirect pathway. This equation allows us to calculate any one unknown value if the others are known. Let's perform a calculation for the lattice enthalpy of sodium chloride. We'll use the equation we just derived. We need the enthalpy of formation, atomization of sodium and chlorine, the first ionization energy of sodium, and the first electron affinity of chlorine. All these values are provided in the IB Chemistry Data Booklet. Plugging these values into our equation, we can solve for the lattice enthalpy. Simplifying the right side gives 377, so negative 411 equals 377 plus the lattice enthalpy. Rearranging to solve for lattice enthalpy, we subtract 377 from both sides, giving a final value of positive 788 kilojoules per mole. This large positive value confirms the strong ionic bonds in NaCl. Now let's tackle a more complex Born-Haber cycle for a compound with divalent ions, magnesium chloride. The cycle for MgCl2 involves more steps because we are forming a 2+ cation and two 1-gal anions. We need 2 ionization energies for magnesium and 2 moles of gaseous chlorine atoms. So, we must double the atomization enthalpy and electron affinity of chlorine in our calculation. We also need to include the second ionization energy for magnesium, which is always much larger than the first because we are removing an electron from a positively charged ion. The overall equation, based on Hess's law, is the sum of the enthalpy of formation and lattice enthalpy on the direct path, equal to the sum of all the individual steps on the indirect path. A common tip: the atomization enthalpy of a diatomic element like chlorine is half its bond enthalpy. If you're only given the bond enthalpy, remember to divide it by 2. We can use Born-Haber cycles to calculate other unknown values, not just lattice enthalpy. Let's work through an example from the practice problems. Suppose we want to find the bond enthalpy of the Beer-Beer bond. We are given the formation enthalpy, atomization enthalpy of magnesium, both ionization energies for magnesium, lattice enthalpy, vaporization enthalpy of bromine, and the first electron affinity of bromine. We need to identify the bar-bar bond enthalpy within the Born-Haber cycle equation. It's related to the atomization of bromine. Bromine is a liquid at standard temperature, so its atomization involves 2 steps. First, The liquid must vaporize, and then the gaseous Br2 molecules must be atomized by breaking the bond. So, the total enthalpy of atomization for two bromine atoms is the sum of vaporization and bond enthalpy. Therefore, 2 times the atomization of one Bohr atom is the vaporization enthalpy plus the bond enthalpy. The full Born-Haber cycle equation is: formation of MgBr2 is equal to atomization of Mg plus atomization of Br2 plus the first and second ionization of Mg plus 2 times the electron affinity of Br plus the lattice enthalpy. Let's substitute all the known values and solve for the bond enthalpy. After performing the calculations, we find that 476 equals 1904 plus the bond enthalpy. This means the bond enthalpy is 476 minus 1904, which is negative 1428. However, bond enthalpies are defined as the energy required to break a bond, which is an endothermic process and should be positive. This indicates a potential issue in the provided data or the problem's phrasing. The enthalpy of solution is another important concept. It's the overall energy change when 1 mole of an ionic compound dissolves in water. Dissolving is a two-part process. First, the ionic lattice must be broken apart. This requires a large amount of energy, which is the lattice enthalpy. Second, the separated gaseous ions become surrounded by water molecules, a process called hydration. Water is a polar molecule, and the partial charges on its oxygen and hydrogen atoms are attracted to the full charges of the ions. The hydration enthalpy is the energy change when 1 mole of gaseous ions is hydrated. This process releases a significant amount of energy, so it is exothermic. The overall enthalpy of solution is the difference between these two. If the energy released by hydration is greater than the energy required for lattice breakdown, the overall process is exothermic and the solution will get warmer. We can represent the solution process using an enthalpy cycle, similar to a Born-Haber cycle. This cycle for sodium hydroxide starts with the solid compound in water and has 2 pathways to the dissolved ions. The cycle shows that the enthalpy of solution is equal to the lattice enthalpy plus the 2 hydration enthalpies for Na plus and OH. The sign of the enthalpy of solution is a rough guide to solubility. A negative DH Degsol often, but not always, suggests the compound is soluble. For example, sodium hydroxide has a lattice enthalpy of plus 887 kJ/mol and hydration enthalpies of 405 for Na plus and 510 for OH. The sum is negative 28, indicating it's soluble. This is a good time for a call to action. If you're finding these concepts challenging, contact DAR tutors for personalized expert tuition in IB, A-Level, and IGCSE chemistry. We can help you master these topics. Returning to our topic, while enthalpy of solution is a useful indicator, solubility is more accurately predicted by a change in Gibbs free energy, which we will study later. Let's work through one more comprehensive example. The Born-Haber cycle for Na2O. We need to construct a cycle for sodium oxide. This compound contains 2 Na plus ions and 1 O2 ion. We'll need 2 ionization energies for sodium, 2 moles of sodium atoms, and 2 electron affinities for oxygen. Here are the enthalpy values we'll use. Note that the first electron affinity of oxygen is exothermic, but the second is highly endothermic because we are forcing an electron onto an already negative ion. Now let's write out the full Hess's law equation for this cycle. It's the sum of formation enthalpy and lattice enthalpy equals the sum of 2 times sodium atomization, 2 times sodium ionization, oxygen atomization, 2 electron affinities for oxygen, and the lattice enthalpy. Let's substitute the values. We calculate the sum of all the individual steps on the right side of the equation, which comes to positive 19p8 kilojoules per mole. Rearranging to solve for the lattice enthalpy gives us negative 414 minus 1948, which is negative 2362 kilojoules per mole. Remember that by definition, the lattice enthalpy is the energy required to break the lattice and is therefore an endothermic process. The textbook answer of positive 2362 kJ/mol is the correct value for the lattice enthalpy, representing the energy absorbed. Finally, let's consider a qualitative question. Which has the higher lattice enthalpy, sodium chloride or magnesium chloride? To answer this, we need to refer back to the factors that influence lattice enthalpy. We know that lattice enthalpy is directly proportional to the product of the ionic charges and inversely proportional to the sum of the ionic radii. Let's compare the ions in NaCl and MgCl2. In sodium chloride, the ions are Na plus and Cla, with charges of +1 and 0.1. In magnesium chloride, the ions are Mg2 plus and Cl, with charges of +2 and G1. The radius of Mg2 plus is smaller than Na plus because Mg has one more proton in its nucleus, but the same electron configuration as Na plus. The chloride ion, Cll, is common to both. Magnesium chloride has a charge product that is twice as large as sodium chloride and a smaller cation radius. Both these factors lead to a much stronger attraction and a higher lattice enthalpy. Therefore, magnesium chloride has a significantly higher lattice enthalpy. We've now covered Hess's law, enthalpies of formation and combustion, and used Born-Haber cycles to calculate lattice enthalpies and other energy changes. You should now be confident in applying these concepts to solve IB/HL-level problems. To solidify your understanding, here are 5 IB-style practice questions. Pause the video and attempt them before I reveal the worked solutions. Question 1 asks you to calculate a reaction enthalpy using formation data. Remember to use products minus reactants and ignore elements. Here are the required formation enthalpy values. Pause now to try it. Question 2 asks for a reaction enthalpy using combustion data. Be careful with the formula here, reactants minus products. Pause and try this problem. Question 3 is about atomization enthalpy. Remember the definition. Write down the equation for the atomization of calcium. Pause now. Question 4 asks for the second electron affinity of sulfur using a Born-Haber cycle. This involves multiple steps. Here are the data you'll need. Pause the video to work through the calculation. And finally, question 5 is a qualitative comparison. Think about the ionic charges and radii. Pause to consider your answer. Welcome back. Let's review the solutions. Solution to Q1. The formula is products minus reactants. We have 2 moles of SO3 as the product, so we multiply its formation enthalpy by 2. We subtract 2 moles of SO2 from the reactants. The oxygen is an element, so its formation enthalpy is 0. Solution to Q2. This time, the formula is reactants minus products. So we add the combustion enthalpies of carbon and hydrogen and subtract the combustion enthalpy of methane. The final answer is -75 kilojoules per mole. Solution to Q3. Atomization is forming 1 mole of gaseous atoms from the element in its standard state. For calcium, which is a solid, the equation is K(as) goes to CaG. Solution to Q4. This is the most challenging. We set up the Born-Haber cycle equation. After substituting all the known values and simplifying, we get -347 equals 5780 plus the second electron affinity of sulfur. Solving for it gives a positive value of 6127 kilojoules per mole, which is expected for adding an electron to a negative ion. Solution to Q. Both compounds have +1 and 1 ions, so we compare the radii of the cations. Rubidium is below potassium in the periodic table, so the Rb plus ion is larger than the K plus ion. Because lattice enthalpy is inversely proportional to ionic radius, a larger radius means a weaker attraction and a lower lattice enthalpy. Therefore, RbCl has a lower lattice enthalpy than KCl. That brings us to the end of this lesson on Hess's law and Born-Haber cycles. We have met our objectives by applying Hess's law using formation and combustion enthalpies, constructing Born-Haber cycles, and calculating unknown enthalpy changes. These are crucial topics for IB Chemistry HL, and practice is key to mastery. Keep working through problems and revisiting the Hess cycles to build your confidence. Once again, thank you for watching. For more in-depth explanations and personalized support, please contact DAR Tutors.